In this section, we're going to learn about two different topics, the greatest common divisor and the least common multiple. We're going to start with the greatest common divisor. A lot of times we shorten that to the GCD, or sometimes you might remember it as the GCF. That stands for the greatest common factor instead of divisor. And what this means is the greatest whole number that divides any of the given numbers that you're asked to find it. Usually it's 2, but it could be more than that. So it is the greatest whole number that divides the given numbers. So for instance, the greatest whole number that would divide both 12 and 40. There are several different methods to find these. We're going to go over 2 different methods, but there are others that are available. One thing that gets people is just the wording. This is called the greatest common divisor or greatest common factor. So we see greatest is the first word that pops in, but our answer should always be smaller. That's because we're dealing with a divisor or factor. Those are same thing. So factors and divisors are smaller than the given numbers. So anytime we're dealing with a GCD, our answer should be smaller than the given numbers. Even though it says greatest, that divisor and factor are where I really know what I'm dealing with here. The reason it's called greatest is because there could be lots of divisors. For instance, if we're looking down here at this first one, the 12. The divisors of 12, any number that divides 12, 1 divides 12, 2 divides 12, 3, 4, 6, and even 12 divides 12. Those are all divisors. We want the greatest one in this list that would also divide 40. So I'm going to list out all of those divisors of 40. I like to just put mine in order. That way I can see where the greatest one is. But since this isn't a set, the order isn't important. 1 divides 40, so does 2, 4, 5, 8, 10, 20, and 40. Those are all the divisors of 40. Now I can take my list and I can find the numbers that appear in both of them. So they both have 1, they both have 2, and they both have 4. So those are all the common divisors. I want the greatest of all of those. So the greatest is 4. So we could say the GCD of 12 and 40, sometimes it's written like this, is equal to 4. And that is the intersection of sets method. That's usually the first method that we have when we're finding these GCDs, or even when we get to the least common multiples, the LCMs. However, we also can use the factor trees that we previously learned. So we're going to look at that method now. So for both my numbers, I'm going to make my factor tree. So make a factor tree for 108. Remember, you can start with any number that would divide 108. It's even, so I started with 2. 108 divided by 2 is 54. Again, 54 is even, so I just divide it by 2. 54 divided by 2 is 27. 27 is odd, so I couldn't use 2. I tried 3. So the prime factorization for 108 is 2 squared times 3 cubed. I'm going to do the same thing for 72. Make a factor tree. Again, I saw 72 was even, so I did 72 divided by 2 to get 36. We don't have to do our factor tree exactly the same way. We're going to get the same prime factorization in the end. 36, I immediately thought 3, but you could have done 2 as well. It doesn't matter. We're going to get the same answer in the end, no matter how you decide to do your factor tree. The prime factorization for 72, there are 3 2s and 2 3s. So that's the prime factorization. That's the first step. Now to find the GCD, we're going to multiply the prime factors they have in common. They're only the bases that they each have. So these both have 2. But I want to go with the smallest. Again, remember my answer should be smaller. So that's what they mean by they both have in common. Both of these have 2's. 108 has 2 squared, that's 2 times 2. 72 has 2 cubed. That's 2 times 2 times 2. What they both have in common is 2 squared. So you look for the smallest exponent. So that would be 2 squared. Same thing for 3's. We're going to look for that smallest exponent. That is because we need what they both have in common. They both have 3 times 3. They don't have 3 times 3 times 3. So they both have a 3 squared. And then I can multiply 2 squared times 3 squared to get 36. So the GCD of 108 and 72 is equal to 36. All right, I'm gonna let you pause the video and see if you can write out the prime factorization for 140 and 320. Might have to squeeze it on there because there's not a whole bunch of a lot of space on that page. So go ahead and pause the video and see if you can get the GCD, or sorry, just the prime factorization for 140 and 320. All right, let's see how you did. Again, doesn't matter if your factor tree looks different from mine. We're going to get the same prime factorization in the end. That's what's nice about factor trees. The prime factorization for 140 is 2 squared times 5 times 7. Do the same thing for 320. Making my prime factorization. I'm going to get 1, 2, 3, 4, 5, 6, 2 to the 6 times 5. Now I'm going to use the GCD, and to do that, I'm going to use anything where they have the same base. So only the bases that they both have. So in this case, 7 isn't in both of my prime factor trees, so it will not show up in my GCD. What this means is 7 does not divide 320. And you can test that in your calculator. 7 doesn't divide 320. So that's why I don't use it. I do see that 2 divides both of these numbers because there's a 2 in both of them. But 2 squared is smaller than 2 to the 6. So I'm going to use 2 squared. And I also see that 5 divides both of them. They both have the same thing. It's both just a 5. Doesn't really matter where you grab it from. So I get 2 squared times 5. So that's going to be 4 times 5. So my GCD would be 20. You can test this out. 20 divides both 140 and 320.